Alabama STEM Explorers is made possible by the generous support of the HudsonAlpha Institute for Biotechnology, Southern Research, solving the world's hardest problems, the Hawley Family Foundation, Alabama Works, Alabama STEM Council, Alabama Mathematics, Science, Technology, and Engineering Coalition, Alabama Math, Science, and Technology Initiative.
I love aquariums. It's great that you can see through the glass to look at the different animals underwater. You can't do that out in the ocean, though. I wonder how scientists study life underwater where it's really deep. I think I might know who can help us out.
Welcome to Alabama STEM Explorers. I'm Neil, and Cruz and I are here at the Dauphin Island Sea Lab and Alabama Aquarium on the Gulf Coast of Alabama. We're here with Dr. Tina Miller-Way, who is the chair of Discovery Hall Programs for Education and Outreach at the Dauphin Island Sea Lab. Tina, Cruz and I were talking about how you actually explore underneath the ocean surface, in the depths. Can you help us with that?
Oh, I'd love to. You know, I think the ocean's fascinating. There's so much left to learn. The ocean is about 36,000 feet or 11,000 meters deep. And obviously, we can't put on a little mask and snorkel and go all the way down there. So we actually use underwater robots or something called remotely operated vehicles to explore and to work in the deep ocean. Do you want to build one today?
Yeah, sure.
You know, Cruz, we were talking about things that we use to explore under the ocean, and one of those things that we use are underwater robots. And there's lots of different kinds of underwater robots, but today we're going to talk about ROVs. Do you know what ROV stands for?
I don't know what.
Remotely operated vehicles. And I've got a couple here to show you. Want to see?
Yeah.
I want you to look at this one and tell me what you notice.
It's sort of like a
It's heavy.
plane. Oh yeah, this one's really heavy. Same type of propellers. Oh, this one has a camera.
Oh, very good. And what am I holding here?
Wires?
Wires. This is the important part, and this is one of the things that makes an ROV an ROV. It has a cable connecting it to the boat, and we call that a tether, right? So you're right. I mean, ROVs have a tether, they have motors, and then they have some way that we can see what the ROV is seeing, like a camera, okay? You want to build one?
Yeah.
Well, let me show you something. We got another one here that is hand-built, but I want you to look at this and tell me what you see that's similar to what you saw on these.
Propellers.
Awesome.
More wires.
And what do we call that wire?
A tether.
Right, very good.
There's this thing right here. Sponges.
These are actually buoyancy, right?
Okay.
So we build these things. If you're putting a couple $1,000s or $1 million into one of these ROVs, you want it to be slightly buoyant, right? That means floating to the surface. Yes. Because if something goes wrong and you lose this tether, it becomes disconnected and it sinks to the bottom of the ocean, what's going to happen?
It goes away, basically.
Right.
You can't really retrieve it.
Right. And, you know, do things ever go wrong at all?
Yeah.
Yeah, they do. So to really figure out how to build one, which is what we're going to do today, we have to talk a little bit about buoyancy. You cool with that?
Yeah.
What do you think buoyancy is?
Stuff that floats, maybe?
Yeah, so making things lighter than water, right? So let me show you something. Standard styrofoam cup. Is it heavy?
No.
No, it's light, right? So what that has in it is air. Air is part of the material that makes up styrofoam, right? The same reason that you cannot dive down to 5,000 feet in the water is why?
Because we have air in our lungs.
Exactly. And that pressure, when you go deeper in the ocean, that pressure will compress that air and it'll kill us, right?
Yes.
But look what it does to something that has air in it. So this is the exact same cup as that, only one that went down deep in the ocean on the outside of an ROV. What do you see?
Oh, wow. That's definitely smaller, compressed.
Exactly.
Wow.
Yep, it compressed all that air and made a perfect little cup just from something that looked like that, because that air was compressed. What you saw as the sponges or the pool noodles on our ROV is what keeps it buoyant from sinking to the bottom, in this case of the water out here in the Gulf of Mexico. Yep. Cool. Well, let's do this. Let's grab our pieces and start building. What do you think?
Yeah, that sounds really exciting.
Some things to keep in mind, right, is you got to have your motors. That's what makes it move. So these are the motors that you're going to use, right? Well, where you put those motors is important. You want to go forward and you want to go backwards, but you also want to go up and down, right? So you got to think about that when you figure out where to put your motors. And then this is your control box. That's already wired for you. Okay. And that is the same thing that this is, right? It just looks a little different. That's how you make the motors go. And then importantly, you gotta have some power, right? You gotta have batteries to make it go. And that's a big deal in the deep sea, is getting batteries. So we have easy batteries over here. That's our power source. And this is your connector to the power source. So we'll build the frame with the motors and then we'll plug it in and see if it goes. Does it sound like a plan?
Yeah.
All right, let's start building. What can I do to help? What are you thinking about?
Square maybe.
Okay.
Sort of like that one.
Yeah. So let's give you some corners, huh?
Yeah.
All right. Oh, black. Yeah, so then you're creating that space, right, within the frame that we're going to put those motors. Now, the way these motors are set up is they have a little joint here, and that's the way that you're going to hook them to the frame. So let's think about that. What is a way that you can hook those motors to the frame? Oh, there's an idea. Okay.
Yeah.
So you want something to hold that motor. Maybe if you did that and then take that motor. Yeah. Well, I tell you, we've done the wiring for you. So, you know, each of those switches controls one of the motors. So now I'll hold that and you keep building. You've got a left motor and a right motor. Look at this one here, right? We've got one on each side so that we can make it curve left or curve right when we're flying it. You know, and that's a funny thing. We don't talk about driving an ROV, we talk about flying an ROV. Even though it's in the water, it's still flying. So what are you thinking?
If we maybe do that.
Okay.
We could put this here. Yeah.
Okay, so that could be our up-down motor, right? So now we just have to build one kind of on the other side, right, to sort of mirror what you've already built here. So maybe I can help you out, if you're okay with that, putting a couple pieces in.
Yep.
Okay, boy, it's beginning to take shape. Yeah, you just gotta squeeze that stuff together. What else you need?
Gonna do this first, right here. And I'm gonna get a purple right here.
Okay.
Connect this.
All right.
Like that, and
well, now we got one more motor to put on. Where are we gonna put that? You thinking ahead?
Yeah.
Got a plan. Got a plan.
I'm gonna twist this.
Doesn't have anything to hook into right here. Is that okay?
Yeah, that's fine. That'll be fine. That'll be fine. Actually, no. Let's do this first.
You know, when we're putting equipment in the ocean, we want it to be as strong as possible. So I see something that's missing here.
Yes.
What do you see that's missing?
This part right here.
There you go. Yep. So let's complete that out. That'll bring some strength to the frame, right? Here's your black. Now on this one, you connected it to this that gives it strength, right? Here and there, you just have that blue piece going up. And here, you've used that connection for the motors. So maybe if we had a 4-parter, you know, it's got 4 ways of plugging in. Putting that there would give it strength. You'd still have 1 for the motor. You'd have 2 to hook it to the cross brace, but then you'd have 1 to hook it to the bottom brace too. And that would give it extra strength. All right, well, let's try it this way and see if it holds. Put it right back into there, right? And see if it holds when we put it in the water, right? So we've got our left motor, our right motor, we've got our up and down motor. So I think we're set. You want to plug it in and give it a go? Make sure it's working before we put it in the pool?
Yep.
So here's the connection between the motors and the control box, also known as the, do you remember that?
The tether.
Right,
yes.
Exactly. But the one thing we're missing right now is the connection to the power source. So that battery right there is our power source for today. So we're going to plug that in.
It in right here. Yep.
Now, if everything's plugged in right, when you flip the switches on that control box, the motor should turn. Let's try it. The battery source is on, so there is power flowing to your control box, and you are the ROV pilot now with that. And just flip it up or down. There you go.
Yep. Yeah, this is really cool.
We got it all working, yep. Now you notice when you flip those switches that the motors can go one way, but they can also go the other way, right?
Yes.
So that's important to remember when we take it out to the pool and we want to try to drive it, right? Out in the pool and drive it through around obstacles or do missions, carry out tasks in the water.
I'm the Senior Research Laboratory Manager here at the Dauphin Island Sea Lab. I technically work for the University of South Alabama, and so you could say that I am in academia. The main part of my job is teaching, but I don't actually teach in a classroom, so I get to teach in a laboratory or on a boat. But one of the coolest things about my job is that I get to do research. This is our remotely operated vehicle. It's an Outland 2000. It's a small commercial class ROV, but we actually use this in research. So we use this to study the population dynamics of fishes. We're looking at abundance and distribution. We get to look at the size of the fish that are down there, and then we can also look at movement of the fishes and behavior of fish underwater. So I drive this ROV mostly offshore Alabama. So Alabama's waters near shore are pretty cloudy. You really can't see too much. If you've been to the beach in Alabama, you try to swim around or snorkel, you notice that it's not super clear. So most of the time we're working anywhere from 10, 20, all the way out to 90 miles offshore. And what we mostly study is Alabama's artificial reef zone. So what's really cool is the state of Alabama actually puts a lot of resources into its fishery and creates habitat for fish to live on. And so I get to go out to these different habitats and examine the reef type. So we look at different types of reefs. They might be rubble, rock rubble. They could be artificial reef pyramids. We can look at those different habitats. We can count the fish on the reef, see what different types of fish there are, and actually look at the size of the fish using these lasers. So anyone interested in becoming a marine biologist, a fisheries biologist, a fisheries researcher, an offshore explorer, I would say at a very young age, just read and learn as much as you can about the oceans. So study math, science, learn about technology, learn as much about computers as possible, but you don't have to live on the coast to do this type of work. So I would just say, learn as much as possible, visit on vacation like the Dauphin Island Sea Lab, and read and study as much as you can.
Okay, Cruz, we're almost ready to deploy it, which is a fancy way for saying we're going to put it in the ocean and fly it. We got to think about one thing. If you're going to carry out task in the ocean, whether it's, welding something, fixing a leaking oil well, or whether it's observing fish or collecting animals that we've never seen before. So we've got to add something like an arm or a claw or something on that ROV frame. So, and the way that we do that in the ocean is we use the power of hydraulics. It's a fancy word, simply meaning that we're moving fluid. We are causing motion by making fluid move. And I have this really cool little model that I want you to play with that demonstrates hydraulics. So I want you to play with those plungers and tell me what you observe when you move them.
So we have this red one right here.
And what happened when you move that?
Moves it left and right.
There you go.
And then this green one here moves its waist. This blue one goes up and down.
There you go.
And then the yellow one opens and closes.
The grabber arms. All right. So you're right. Well, I'll tell you, this is just water that's been colored just so that you can see the differences. But you're right. By moving those plungers, you've caused motion in any part of our model here. So I'm going to challenge you. I want you to pick up that ping pong ball and with your model, and I want you to drop it in that tower.
Okay. And
Nope, he's caught it.
got it.
Yep.
And
What do we say in the ocean? You got to retrieve it.
And
bingo! Very good, very good. So, I mean, just by the simple movement of water, of fluid, right, you can do things with an arm. And so we would develop a hydraulic arm to put on our ROV so that when we took it in the ocean, we could go and do things with it, right? So what can we use to make things float?
sponges, pool noodles.
Pool noodles.
Pool noodles.
Yeah. What else might we use? What if tell me what would happen if I took a closed container of air and I'm in a swimming pool and I'm going to hold it down here and I let go. What's going to happen to that bottle?
I guess it's going to float up.
It is. Why?
Because there's air in it.
Exactly. So, you know, we could use this too. We could fill this with air. Oh, I just did, didn't I? And then strap it to the side of our frame. So there are a whole bunch of different kinds of things that we can use for buoyancy on ROVs. We have an example here of catch. Did you think I was throwing a brick at you?
No, not really.
No? It's pretty light, isn't it?
Yeah.
This is what we use in real commercial ROVs for buoyancy. It's called syntactic foam. And syntactic foam is basically glass spheres filled with air, right? Air is less dense. That's what we use for buoyancy.
It's pretty solid.
It's pretty solid, right? That glass is all glued together. So let's put some buoyancy on your ROV and get ready to go deploy it. What do you think?
I think I'm ready.
All right, there you go. All right, so Cruz, you're going to be adding some buoyancy to your ROV. We've got some pool noodles. You know, have you ever played with a pool noodle?
I have.
If you're at the bottom of the pool and let go, what happens to it?
It basically just comes right out.
There you go. So we've just cut them into sections, right, to use on your frame. So why don't you add buoyancy to your frame. And of course, when we get out to the pool, we'll adjust how many pool noodles you'll have on there, because again, we build ROVs to be slightly positively buoyant.
Put one right here.
Good. Do you think it's important to have it balanced?
Yes.
Why is that?
So it doesn't tip over.
Or do this,
Yeah.
right? You'll have one side that's more buoyant than the other, and so it'll be uneven in the water. You know, and one of the tasks that we use ROVs for is hovering and looking at things, and if you're like this, you know, the world's gonna look cockeyed.
Yeah.
Now I'm interested why you didn't put the buoyancy down here. Why is that? What were you thinking about?
Because if I did, it would basically just tip over.
Yes, right. You want your buoyancy on the top. If you put it here and not here, the whole thing would go whoop, right? And be upside down, if you will.
So
Right, and you know, there's a
closer.
couple of different ways for actually figuring out how much buoyancy you need, right? You want it to be, if you made it too buoyant, it can't dive in the water. It can't go down, which is what you're building it for, right? So you don't want to put too much buoyancy on, but you also want it to be slightly buoyant so that if it, you know, becomes disconnected, it'll float up to the top. So you can actually weigh all this stuff and calculate using math how much buoyancy you actually need. With these pool noodles, we just go out and we test. We add some more, we take some away, we retest, and that's also a way that engineers work. Cool? All right.
Yeah.
All right, are you ready for the maiden voyage? You have a name for it?
The Voyager?
Okay, oh, I like it, I like it. All right, the maiden Voyager, let's remember what we have here. You've got the left motor and the right motor. Are they both spinning? There you go.
Yep.
And you've got that one. What does that one do?
It goes up and down.
Right, and then we've added what?
We've added buoyancy.
Okay, and
That makes it float.
all right, but not enough that it's going to make it stay at the surface. So you should be able to dive down. And of course, you put the frame together that gives something to move so that it can go into the ocean and carry out tasks. So we're gonna let go. I'm gonna be your tether holder. Oh, look at that.
So I can use these to go backwards and forwards. It's going forwards right now. I'll stop that. I'm gonna come up a little bit.
Okay.
I'm gonna turn it.
You know, and these things, each one is balanced differently, so it takes a while to practice to get them, you know, to fly the way that you want them to. And so there are people that do this for a living. In a real shipboard situation, you'd be sitting in a control room or something of the ship, and you'd be flying this thing through a computer screen. But of course, we want to see it actually move, and it's more fun when you can do that, right? So the Dauphin Island Sea Lab is the marine research and education facility for the state of Alabama. We were funded by the state to bring ocean literacy to students, to learn new things about the ocean, and importantly, to manage the ocean resources for Alabama in a wise way. The Sea Lab really consists of 3 parts. Discovery Hall part is the education and outreach part. We have another unit called University Programs that is undergraduate education and graduate education, but also research. So those researchers are out there in the field learning new things every day. And then we have the aquarium that brings those animals to the public. It has a touch tank for stingrays. Right now it's got a shark in it, so that's pretty cool. And kids usually really love sharks and rays. And octopus are also very popular among students. And they're fascinating creatures. They're invertebrates. They don't have any bones inside of them. And so they can be escape artists and get out of the tank if we're not careful. So you want to learn more about the ocean, you're excited about that, right? You've got to read stuff, you've got to visit, you've got to go out and be curious about that, because unfortunately we don't teach enough about the ocean in our classrooms and that kind of stuff. So go to aquaria and visit and ask questions of the people that are taking care of those animals and learn more. You know, now there's a lot of stuff online, a lot of really good material online. Here in the National Oceanic and Atmospheric Administration, we have a ship called the Okeanos Explorer that just goes out and explores the ocean because there's so much left to learn. So be curious and follow your curiosity however it leads you.
Thanks for watching
watching Alabama STEM Explorers. If you missed anything or you want to watch something again, you can check out our website at alabamastemexplorers.org. Maybe you have a question we could answer here on the show, and you might grab a cool t-shirt. Feel free to send us a video question or an email on our website, alabamastemexplorers.org. Thanks again for watching. We'll be back next week.
Alabama STEM Explorers is made possible by the generous support of the HudsonAlpha Institute for Biotechnology, translating the power of genomics into real-world results. Southern Research, solving the world's hardest problems. The Hawley Family Foundation, established to honor the legacy of Brigadier General Everett Hawley and his parents, Evelyn and Fred Hawley, champions of servant leadership. Alabama Works, a network of interconnected providers connecting business and industry needs to a highly skilled and trained workforce. Alabama STEM Council, dedicated to improving STEM education, career awareness, and workforce development across Alabama. Alabama Mathematics, Science, Technology, and Engineering Coalition for Education, advocating for exceptional STEM education in Alabama. Alabama Math, Science, and Technology Initiative, the Alabama Department of Education's initiative to improve math and science teaching statewide.